Hello everyone, I'm Tianyao Huang from Tsinghua University. In this video, I will present our ICAS paper. Our paper is entitled as Theoretical Analysis of Multi-Carrier Agile Phase Array Radar. It's a joint work between two groups from Tsinghua University and Weizmann Institute of Science. The co-authors are Nir, Yonina, Xinyu, Dingyou, and Yiming. We divide the presentation into three parts: the motivation, basic idea of proposed CASA, and some simulation results. Complex electromagnetic environment has become a threat to radars. For example, in urban areas, mutual interference between many radars is inevitable. Some military radars could encounter intended hostile jamming. Frequency agile is a promising technology for radars to survive in these environments. FAR changes the carrier frequencies pulse by pulse. In a single pulse, a narrowband monotone is transmitted, which reduces mutual or intended interference. A challenge in FAR emerges in its range Doppler recovery. Compared with traditional wideband radar, FAR is regarded as a subsampling in frequency domain. As a result, the number of observations in FAR is reduced. Therefore, matched filter, which works well in wideband radar, does not fit FAR. Fortunately, compressed sensing proposed for subsampling will solve the range Doppler recovery problem in FAR. However, in some extremely congested electromagnetic environments, for example, there are more radars than available frequency bands. In this case, conflicts in frequency domain is inevitable, resulting further reduction in number of observations. In this case, even compressed sensing doesn't work in FAR. This motivates us to design new frequency agile waveforms, using CASA. The key idea is to increase the number of observations. We achieve this goal by sending multiple carriers and call the new scheme as multi-carrier agile phase array radar, abbreviated as CASA. We will first share the basic concept of CASA and then some theoretical results. In CASA, we select multiple carriers in each pulse, and each carrier is transmitted by a subarray of antenna. Here, we don't use each antenna to transmit all the selected carriers because this would result in complex hardware. In different pulses, both frequencies and subarrays are chosen differently, which also introduces spatial agility. Compared with the standard FAR, CASA increases the number of observations. This will enhance the survivability of the radar under extreme electromagnetic environments. Another advantage is that the spectral and spatial agility can be used to convey communication bits, leading to a joint radar communication system. While this paper focuses on the radar performance, the joint radar comm will be discussed in another paper. Since only a subarray is applied for transmitting each carrier, there's a reduction in antenna gain, resulting loss of SNR. We will show in the simulations that the increased number of observations dominates the SNR loss in some extreme environments. The received signal model can be written as a linear equation. Here, the vector x is unknown to estimate. Each entry in X represents the scattering intensity of a target in a certain range Doppler cell. The colorful box here denotes a non-zero entry, meaning that a target exists in the cell. There are only several targets, so the vector X is sparse. The observations correspond to echoes of different pulses. Each pulse contains several observations relying on the selected frequencies. So we see that CASA has more observations than FAR. In extreme cases, strong interference makes some observations unreliable. We regard them missing. The model becomes this. We use L1 norm minimization to solve the equation by exploiting the sparsity in X. In the model of CASA, we will show that the performance of CS algorithms is guaranteed. Our analysis is based on mutual coherence. When the coherence is the coherence of a matrix is defined as a maximum normalized inner product of two different columns. When the coherence is no larger than this term, where S denotes the number of non-zeros in X. L1 norm minimization provides unique solution. We then analyze the coherence of the measurement matrix in CASA. We prove that L1 provides unique solution with high probability when the following holds. Here, S is the number of targets and K is the number of selected frequencies in each pulse. We find that for larger K, more targets are supposed to be recovered. U is the probability that an observation is not missed. M and N are radar parameters. We then show some simulation results. We compare the proposed CASA with several other schemes. In CASA, two frequencies are sent in a single pulse. We also proposed wideband multi-carrier agile radar, WMAR, previously, where we select the same two frequencies. However, both frequencies are simultaneously transmitted by each antenna unit. Therefore, the hardware of WMAR is more complex. CASA uses each antenna to send only one carrier, which reduces the complexity but has loss in SNR. We also compare with FAR, which transmits a single frequency. We also compare the fixed frequency radar, which is the traditional pulse Doppler radar without frequency agility. Thus, it is vulnerable to interference. We first compare the performance of target detection under clutter. The clutter to noise ratio is 30 dB, and we set the false alarm probabilities to be a constant. Two scenarios are considered, one without interference, where U equals 1, and the other one having strong interference and part of the pulses are missed, where U is less than 1. We depict detection probabilities versus SNR. From the fig, we see that when there's no pulse missing, CASA has an SNR loss than the rest schemes. When there are pulse missing, FAR fails, the detection rates are zeros, while multi-carrier schemes still operate, and CASA has SNR loss than WMAR. But we should note that CASA has a more simple hardware architecture. We conclude here, CASA improves detection performance of FAR under severe interference. We also consider the range Doppler reconstruction performance versus the number of targets. In noise-free scenario, KESAR has close performance to WMAR, and the multi-carrier radar performs better than FAR. This coincides with our theoretical result, which indicates that the number of recoverable targets increases with the number of selected frequencies. In noisy scenarios, we have similar results. When there's no interference, the performance is close. On the strong interference, multi-carrier works better. We conclude this paper, we propose KESAR, which transmits multi-carriers to enhance the robustness against interference, and it implements spatial agility to reduce the hardware complexity because it avoids sending instantaneous wideband signals. It also has provable performance, and it outperforms FAR, especially in extreme electromagnetic environments. We would like to mention again a byproduct of KESAR, which is dual function radar communications. You can use index modulations in both the frequency and the spatial domains to convey communication bits. Thank you for watching our video. You may scan these QR codes to access the full papers on KESAR and on the dual function radar communications using KESAR. These papers are put on the archive websites. Okay, here's the slides. Again, thank you for watching our video. Have a good day.